we look back at how people once tried to predict the future using Newton's laws, one thing becomes clear. Not every system behaves the same way. For a long time, there was a strong belief that if we understood the rules and forces behind the universe, we could predict everything that would happen next. As you already learned, that idea was shattered in the early 1960s. Scientists started to see that total predictability wasn't realistic. They began grouping systems into four types: simple, complicated, complex, and chaotic. Each one carries its own level of unpredictability, difficulty, and connection between parts. We'll walk through each type to see what sets them apart. We'll look at systems that follow clear patterns to those that twist and shift in ways we can't always see coming. If there is a system on Earth, it falls within one of these types. So let's start with a simple linear system. We'll characterize these systems as ordered predictability. Simple linear systems work in a very straightforward way. One thing causes another, and the results are usually predictable. If you change the input a little, the output changes in a consistent way. Newtonian mechanics is a well-known example where force and motion follow clear linear rules. A light switch is a good example of a simple system. When the switch is flipped up, it completes an electrical circuit and the light turns on. When it is flipped down, the circuit is broken and the light turns off. The relationship between cause and effect is direct, consistent, and highly predictable. Given the same conditions, the same action produces the same result every time. That is what makes it a simple system. Next, we'll discuss the second of our four types of systems: complicated linear systems. We'll characterize these systems as elaborate structures. As systems grow more detailed and layered, they can still behave linearly and be reliably predictable. A complicated linear system has many parts. Each part follows simple and predictable rules. But when all these parts work together, things get harder to track. The behavior of the whole system can still be predicted, but it takes more effort to do so. The rules are still linear, but the number of moving pieces adds complexity to the mix. Take a car engine, for example. It's a complicated machine made up of many parts, all working together. Each part plays a role, and the engine depends on all of them working in sync. Imagine someone forgetting to reinstall one of the spark plugs during a repair. That small mistake becomes the input. The missing spark plug causes a clear, predictable problem in the engine, resulting in misfires, poor combustion, and a drop in power. The relationship between the input and the output is still there, but the effects spread across the system. In systems like this, it's still possible to trace the cause and effect, but it takes more attention to see how one missing part can ripple through the whole thing. Our next system we'll call complex nonlinear systems. Let's characterize these systems as emergent properties. Complex systems are different from simple or complicated ones. They involve nonlinear relationships, which means you can't figure out the whole system just by understanding its parts. Even if you know exactly what each part does, that still won't tell you how the entire system will behave. In these systems, things don't move in straight lines. The parts interact in ways that create new patterns and behaviors. These systems often form their own structure over time, and they do it without a central decision maker giving instructions to the system. We'll call our fourth and final system chaotic nonlinear systems. Let's characterize these systems as sensitivity to initial conditions. These systems sit at the far end of the nonlinear spectrum. They're known for being extremely sensitive to starting conditions. Even a tiny change at the beginning can lead to very different outcomes down the line. This makes long-term prediction nearly impossible. Think back to Ed Lorenz's work in weather systems and the divergence in Mark's life after turning left or right. Understanding these kinds of systems matters. As we explore the range of systems from simple and linear to complicated, complex, and finally chaotic, we start to see the many different ways cause and effect unfold. And that matters to every human brain because we all live inside systems like these, whether we realize it or not. This is the world Right Side Blind would like to introduce you to. It's messy, It's unpredictable, it's filled with complexity, but inside all that chaos, there's something worth discovering, something true. Get ready because we are about to realign what you have been taught up to this point. Right side blind is the effect of stressful events in our environment, leading to dysfunction in some human brains. Looking at the world through the lens of four systems does not help the human brain navigate a complex environment. So we'll start back at our original four systems and make changes where necessary. We'll start here with our four systems. Now, because our top two system types are linear, we will not be concerned with those systems. We are now left with only complex and chaotic systems. As a matter of fact, 90% of our world is comprised of these types of systems. These are the systems that challenge us as human beings. They are the ones that seem to disrupt man's search for safety, security, and relative happiness. Our job now is to work from here, as these are our two remaining systems. If you remember from our Part 1 video on complex and chaotic systems, academia does not do a good job of explaining where chaos fits into our complex world. Because of this, we will redefine the role of chaos inside the majestic nonlinear so as to better fit the purpose of right side blind. We will depart from the traditional way nonlinear systems are classified. This is not because the accepted scientific framework is incorrect. Rather, it's because we are asking a different question. Rather than studying systems in isolation, we are interested in understanding the environment as it is actually experienced by the human brain. The brain never encounters isolated weather systems, isolated economies, isolated families, or isolated social networks. It encounters one continuously interacting world. The same goes for isolated complex systems and isolated chaotic systems. We just never experience them separately. For that reason, we will find it more useful to think of complexity as the overarching condition of reality, with order and chaos describing how that complexity behaves from moment to moment. To further this idea, let's look at a visual example of our problem with chaos. To start, we already know that a system is a set of interacting or interdependent parts that function together as a unified whole. So, a complex system qualifies as a system. However, we start to see that chaos has no parts that can function together as a unified whole. Therefore, it cannot be a system. Let's dissect this so we know exactly what is going on. This is Tim. We will use Tim as an example of how chaos is an orphan of nonlinear dynamical systems theory. Tim likes to gamble at the local casino. He usually goes about once a month, and he particularly likes the dice games. Tim has put money down as a wager and is ready to throw the dice onto the felt table. Here is Tim, holding the dice in his fist. We'll now freeze our reality to explain what is happening at this moment. As far as complex systems are concerned, Tim, the dice, the betting table, the people in the casino, the drinks, the lighting, all belong to one giant complex system. Hold on to the thought that the dice now make up part of this complex system, because that will change soon. You see, the throwing of dice is considered chaotic. If this is so, then why are they considered complex when they are in Tim's hands before he throws them? When do they become chaotic? To see this, we will allow Tim to make his throw. At the moment the dice leaves his hands, we will freeze the action again. Believe it or not, those dice that were once part of a complex system in Tim's hands magically become part of a chaotic system in midair. If you haven't seen the problem yet, just hang in there, because you will. So what makes the dice chaotic at this point in time? And why is the behavior of the dice separate from the behavior of the complex system surrounding them? Experts in this field would tell you that the complex system surrounding the dice is not affected by any initial conditions, but the dice are inside a system that is heavily dependent on initial conditions. This means that as soon as the dice were thrown, the end result of the winning number was already determined even before the dice landed, rolled, and settled in place. As long as nothing interferes with those dice in midair, it is a foregone conclusion as to how they will end up. In other words, cause and effect are written in stone. There is nothing going on inside the casino at that moment that can be considered written in stone, except for those two falling dice. Let's look at this another way. As Tim is holding on to the dice, he is ready to throw them in this complex system. He is also ready to throw them in this complex system. He is also ready to throw them in this complex system. He will also be throwing them in this complex system. And he is throwing them as well in this complex system. Right side blind is not an attempt to redefine or replace the established sciences of chaos theory or complexity science. The mathematical foundations of these disciplines are both rigorous and remarkably successful at describing nonlinear systems. Their purpose is to understand how such systems behave. The purpose of right side blind is different. It asks how the human brain can meaningfully orient itself within those same systems. Mathematics can describe complexity, but it cannot tell us how to think, decide, or find perspective while living inside it. Right side blind introduces a conceptual framework intended to bridge that gap. It is not here to replace science. We are simply translating the implications into a way of understanding the uncertainty of everyday life. Chaos theory and complexity science do not describe the same kinds of systems. Their mathematics are different, and their methods are different. But from the perspective of the human brain, they eventually arrive at the same destination: uncertainty. Whether unpredictability arises from sensitive dependence on initial conditions or from the emergence of countless interacting variables, the practical consequence is the same. We must make decisions without knowing exactly what comes next. That is where right side blind begins. So when it comes to chaos, there is a very easy way to understand its place in your life. There is what we'll call perceived chaos. And then there is the actual mathematical chaos that grew out of the work of Edward Lorenz. Perceived chaos is the kind most of us experience. It's that overwhelming feeling that life has become unpredictable, confusing, and out of control. It often happens when the complex adaptive systems around us, such as our families, workplaces, communities, healthcare systems, or financial lives, become so complicated that we struggle to understand what is happening or what to do next. Mathematical chaos is something different. It isn't a feeling, it's a property of certain natural systems. Weather is one of the best-known examples. Tiny differences in atmospheric conditions can grow into dramatically different outcomes, making long-term prediction extremely difficult. The same principles can also be seen in other natural phenomena, such as turbulence and some aspects of wildfire behavior. Both kinds of chaos can affect our lives. A hurricane born from the chaotic dynamics of the atmosphere can threaten us with physical danger. Perceived chaos can threaten us in another way. It can increase stress, cloud our judgment, strain our relationships, and make it harder to make good decisions. Understanding the difference between these two kinds of chaos is important because they require different responses. We can't stop mathematical chaos from existing in nature, but we can learn to better understand and navigate the complexity of the adaptive systems in which we live. Now that we've distinguished between perceived chaos and mathematical chaos, let's turn our attention to where perceived chaos comes from. Unlike mathematical chaos, perceived chaos emerges from our interaction with the complex adaptive systems that surround us every day. Now we are in the land of complexity. To better understand this, let's look at what we'll call the scale of complex dynamics. This scale provides a way of thinking about how complex adaptive systems can behave and feel chaotic. Most of the time, complex systems operate within a region of relative stability. In a few minutes, we'll look at a real-world visual example of this, so you can see how this picture applies to your life. As a complex system moves away from that stable region found in the middle, our ability to understand it, predict it, and respond effectively begins to change. And it's during this shift that perceived chaos can emerge. This is Jim, and this is where our real-world example begins. Jim is an operations manager for a medical supply company. He has a big job with a lot of responsibility. He manages 65 employees. He is responsible for maintaining order in warehouse operations, delivery schedules, inventory, safety compliance, budgets, and supplier relationships. He is confident of his ability to do his job correctly. After all, he has been performing this job for over 10 years now. Most people would simply say his success comes from climbing the learning curve for 10 years. But something deeper has been happening. Over thousands of workdays, Jim's brain has been quietly building an internal model of how his workplace operates. He's learned what usually happens, how problems are typically solved, who to call, what decisions work, and which ones don't. It's not a perfect model, but it's dependable enough that it allows him to predict what will probably happen next and respond with confidence. Later, we'll explore this idea in much greater detail because it plays a central role in understanding why complex adaptive systems can sometimes feel so overwhelming. But there are times at which Jim finds his job a challenge. Most days, his experience and his working model are enough to keep everything running smoothly. But every so often, the number of interacting variables begins to grow. A supplier misses a shipment. 2 employees call in sick. A delivery truck breaks down. The computer network goes offline. Corporate requests an emergency inventory report. One problem quickly becomes 5, and 5 becomes 10. Jim isn't suddenly bad at his job. The system around him has simply become more difficult to understand, predict, and manage. As the complexity continues to increase, Jim begins to experience what we call perceived chaos. Do you remember our scale of complex dynamics? Most of our days are comprised of time in the middle of this curve. However, the right side is where Jim is when things at work become chaotic and complex. The same goes for your life. Whether we are studying Jim's daily struggles or your daily struggles, the picture is the same. Later, you will know the answer as to why our lives slip from equilibrium into disorder. But for now, we'll end this video here by summing up what we've learned up to this point. We know that Right Side Blind is an exploration into the idea that the human brain was never prepared to navigate its nonlinear, complex, chaotic environment. This puts the human brain at risk for stress-related mental illness. To understand this concept, we have identified the different types of systems on Earth and wrapped them all into one system we call the majestic nonlinear. Inside this majestic nonlinear, humans must traverse the rough terrain of chaos and complexity. We also learned that, although chaos is an integral part of nonlinear systems, it seems to have multiple meanings to the human brain. Next, we'll take apart the meaning of nonlinear dynamical systems and why we use this term so often when discussing our world.